Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. In this lecture we will talk about the comparison test to check the convergence of infinite series. So first we discuss what is comparison test, and if we recall that we have seen in previous lectures this type of different series. We have seen that if we have geometric series sigma a into r raised to n minus 1, then geometric series is convergent if and only if absolute value of ratio is less than 1. Also we have discussed that p series in previous lecture, that sigma 1 over n raised to p, n is from 1 to infinity, is convergent if and only if p is greater than 1. So we will be using this series in comparison test. So we should remember that when geometric series converges, when p series is convergent. Okay, fine. So with this in mind, we try to understand comparison test. So there are two types of comparison test. First one is direct comparison test and second is limit comparison test. So in this lecture we will discuss that direct comparison test, and in previous lecture we will go for limit comparison test. So suppose we have some series and we want to check its convergence using direct comparison test. So first requirement is these terms must be positive for all n, or they must be positive for all values of n after some fixed number. That means if n is greater than 0 for all n greater than or equal to say 52, then also we will consider it as series with positive terms. Finite number of negative terms are allowed, otherwise this series must be positive series to apply direct comparison test. Now if we are able to find out another series which is also a positive series, suppose there exists, or suppose we are able to find out another series sigma bn, where bn is also positive for all n, such that an is less than or equal to bn for all n. Here also, if this is not satisfied for finite number of terms, then no problem, but this must be true for all n after some fixed number n. So suppose every term of this series an is less than or equal to bn, which we have selected, then from this we can see sigma an must be less than or equal to sigma bn. So this infinite sum is less than or equal to this infinite sum. Now suppose this series is convergent, that means this sum is finite. Then because this sum is smaller than this sum, it is also going to be finite, and therefore it is convergent. So if this big series is convergent, this series is also convergent because this series is smaller than this series. So if we can find out another series of positive terms, say sigma bn, such that an is less than or equal to bn for all n, then if sigma bn is convergent, sigma an is convergent. So now the problem is how to decide this series. So we will observe the given series and we will try to find out that it behaves like which series. For example, if we have this series sigma 1 by n square plus 1, so we can observe that this series behaves like 1 by n square. So we can consider sigma bn as sigma 1 by n square and we can compare these two series. Now suppose we obtain this type of equality. Suppose every term of given series is greater than or equal to every term of selected series. then this summation sigma an is going to be bigger than sigma bn. So in this case, if sigma bn is divergent, then this sum is going to be infinite. So if sigma bn is divergent, this sum is infinite, and this sum is bigger than this sum which is infinite, so this sum also must be infinite. If smaller sum has infinite value, bigger sum must be going to infinity. So if smaller series is divergent, the series sigma an, which is bigger than this series, is also divergent. So suppose we are given some series sigma an, and if we find out another series sigma bn, of course both series are positive such that an is greater than or equal to bn for all n, then if this series sigma bn is divergent, this is also divergent. So if an is greater than or equal to bn, sigma bn is divergent, implies sigma an is divergent, and if an is less than or equal to bn, sigma bn is convergent, implies sigma an is convergent. So this is limit comparison test. So here I have written the statement of direct comparison test. Suppose that sigma an and sigma bn are series with positive terms. If sigma bn is convergent and an is less than or equal to bn for all n, then sigma an is also convergent. That means if big series is convergent, smaller series is convergent. Now if sigma bn is divergent and an is greater than or equal to bn for all n, then sigma an is also divergent. That means if smaller series is divergent, bigger series is also divergent. So we consider some series to check the convergence by direct comparison test. So first series is sigma n equal to 1 to infinity 1 over n square plus 3. So first we write down nth term. The nth term of given series is an equal to 1 over n square plus 3. N is starting from 1. So here it is clear that an is positive. Clearly an is positive for all n greater than or equal to 1. So given series is a series with positive terms. Now we observe this nth term. So we can see this looks like 1 over n square. So we can try with bn equal to 1 by n square. Suppose we consider bn equal to 1 by n square. N is greater than or equal to 1. And we try to establish the relationship between an and bn. So in an we have n square plus 3 in the denominator, and we know that if we consider n square plus 3 and n square, then this is always greater than n square for all n greater than or equal to 1. So if we take the reciprocal, we have 1 by n square plus 3 is less than 1 by n square, n is greater than or equal to 1. So we have shown that an is less than bn, n is greater than or equal to 1. Now sigma bn, which we have selected, is sigma bn equal to sigma 1 by n square n equal to 1 to infinity. So if you observe, this is a p series with p equal to 2 is a p series with p equal to 2 and which is greater than 1, and we know that p series is convergent if and only if value of p is greater than 1. So sigma bn is convergent. and sigma an is smaller than sigma bn. If we take summation on both sides, sigma an is smaller than sigma bn. So if sigma bn is convergent, sigma an is also convergent. So therefore we can write that by comparison test, sigma an is also convergent. If we wish, we can write direct comparison, or if we write simply comparison test, then also it is fine. So here this is simple application of direct comparison test. We are able to determine the series, another series, such that an is less than bn for all n greater than or equal to 1, and our selected series is convergent, and given series is smaller than selected series, and this series is convergent, therefore this series is also convergent. We consider next series, sigma 7 over 7n minus 2. So second series is sigma n equal to 1 to infinity 7 divided by 7n minus 2. So first we write down the nth term of the series. Nth term is an equal to 7 divided by 7n minus 2, n is starting from 1. Now if we observe 7 divided by 7n minus 2, then it behaves like 1 by n. So we can try bn equal to 1 by n. So we consider, and here obviously all the terms are positive. So given series is positive term series. If you put n equal to 1, first term will be 7 divided by 5, which is positive, and so on, because 7n minus 2 is greater than 0, an is positive for all n, and we select bn equal to 1 by n is greater than or equal to 1, so bn is also positive for every n. Now we can rewrite an equal to, an is 7 divided by 7n minus 2. So if we divide numerator and denominator by 7, here we have 7 by 7, which is 1, 7n minus 2 divided by 7. So here we have n minus 2 by 7. N is greater than or equal to 1. Now it is clear that this n minus 2 by 7 is strictly less than n for all n greater than or equal to 1. So if we take the reciprocal, 1 over n minus 2 by 7 is greater than 1 by n for all n greater than or equal to 1. Now 1 over n minus 2 by 7 is an, and this is bn. So here an is greater than bn for all n greater than or equal to 1. That means given series sigma bn is greater than sigma an is greater than sigma bn. Sigma an was 7 over 7n minus 2, and sigma bn is sigma 1 by n. So if sigma bn is divergent, sigma an is divergent. Now series sigma bn is a p series with p equal to 1, and it is divergent. Therefore sigma an is also divergent. So now we mention that sigma bn, where n equal to 1 to infinity equal to sigma 1 by n, is divergent. This is famous series known as harmonic series, which we have discussed in previous lecture, is divergent series because it is a p series with P equal to 1, and we know that P series is convergent if and only if P is greater than 1. So now sigma Bn is divergent and sigma An is bigger than sigma Bn. So therefore by comparison test, sigma n equal to 1 to infinity is also divergent. Now next series is, let me check what was the next series. It is sigma 1 by n factorial, n is from 0 to infinity. So we now discuss about convergence of last series. It is sigma 1 over n factorial, n equal to 0 to infinity. So the nth term is an equal to 1 by n factorial. Here n is starting from 0. Now for n equal to 0 we have a0 equal to 1 by 0 factorial, which is 1 by 1, which is equal to 1. a1 is 1 by 1 factorial, that is also 1. a2 is 1 by 2 factorial, and it is equal to 1 by 2. And if we compare, okay fine, we write down one more step. a3 is 1 by 3 factorial, and this is equal to 1 by 6. So if we consider 3 factorial, then 3 factorial is 6, and if we consider 2 square, that is 4. So 3 factorial is bigger than 2 raised to 2, that is 4. That means 1 over 3 factorial is less than 1 by 2 square. So here I can write that a3 is equal to 1 by 3 factorial is less than 1 over 2 square. Here I can write that a2 is less than or equal to 1 over 2 raised to 1, because here we have 2 raised to 1 power. So we are trying to decide the behavior of each term of given series. So now fourth term of given series is a4 equal to 1 by 4 factorial, and if we consider relationship between 4 factorial and 2 raised to 3, 4 factorial is 24, which is greater than 8. So 4 factorial is bigger than 2 raised to 3. So therefore 1 by 4 factorial is smaller than 1 over 2 raised to 3. So this pattern will continue if we consider one more term, say a suffix 5. Then a suffix 5 is 1 over 5 factorial, and 5 factorial is 120, which is greater than 2 raised to 4, which is 16. So we can write here a5 is smaller than 1 over 2 raised to 4. Now here again we can rewrite this as a2 is smaller than or equal to 1 over 2 raised to 1. So here I replace 1 by 2 minus 1. Similarly here I can rewrite this power 2 as 2 raised to 3 minus 1. Here also I can rewrite this as 1 over 2 raised to 4 minus 1. And here this I can rewrite as 1 over 2 raised to 5 minus 1. So if I have 5 here, in the power of 2 I have 5 minus 1. If I have 4 suffix, here in the power I have 4 minus 1. If suffix is 3, I have here 2 raised to 3 minus 1 and so on. And this we can rewrite as a1 is equal to 1 can be written as 1 over 2 raised to 0. So that I can rewrite as 1 over 2 raised to 1 minus 1. So if I have, and I can write less than or equal to also. So if I have a suffix 1, I have 2 raised to 1 minus 1. So now we can observe, if we have n equal to 1, that is a1, we have 1 over 2 raised to 1 minus 1. If I have a2, I have 1 over 2 raised to 2 minus 1. If it is a3, I have 1 over 2 raised to 3 minus 1 and so on. So in general, what I obtain is an is less than or equal to 1 over 2 raised to n minus 1. N is starting from 1. For n equal to 1, we have a1 less than or equal to 1 over 2 raised to 1 minus 1, that is 1 over 2 raised to 0, which is 1, and a1 is 1. For n equal to 2, a2 is less than or equal to 1 over 2 raised to 2 minus 1, which is 1 by 2, and so on. So now we will consider bn equal to 1 over 2 raised to n minus 1, n is greater than or equal to 1. So we have obtained this series which is geometric series, and if we write here, we put bn equal to 1 over 2 raised to n minus 1. So here we can write that an is less than or equal to bn, n is greater than or equal to 1. So therefore sigma an n equal to 1 to infinity is less than or equal to sigma n equal to 1 to infinity bn, and our sigma an is starting from n equal to 0 to infinity. So for n equal to 0, first term is 1. So we can write that 1 plus sigma n equal to 1 to infinity an is less than or equal to 1 plus sigma n equal to 1 to infinity bn. So there is no problem for this finite number of terms. There is only one term in the summation. So if this series is convergent, this 1 plus this series is also convergent, and therefore this series is also convergent. So all we have to check is convergence of sigma bn. This is just for understanding. It is not necessary to mention all these things. So an is less than or equal to bn, and now we check what is sigma bn. So now sigma bn, n is from 1 to infinity. This is equal to sigma n equal to 1 to infinity 1 over 2 raised to n minus 1, which is equal to sigma, this we can rewrite as 1 by 2 raised to n minus 1, n equal to 1 to infinity. And we know that this is a geometric series with ratio r equal to 1 by 2, and absolute value of r is 1 by 2, which is less than 1. So therefore sigma bn is convergent, because geometric series is convergent if and only if absolute value of its ratio is less than 1. So therefore sigma bn is convergent, and therefore by comparison test sigma an is also convergent. Sigma an was n equal to 0 to infinity, that is sigma n equal to 0 to infinity 1 by n factorial is also convergent. So in this way we can use comparison test to decide convergence of given series. Another thing is, suppose we have this type of series, say 1 plus 2 plus 3 plus 4 plus sigma n equal to 1 to infinity 1 by n factorial. Then to decide the convergence, if we are applying comparison test, then we will consider Bn equal to 1 over 2 raised to n minus 1, and n he will start from, there are 1 2 3 4 terms here, so here we can consider n from 5 to infinity. So we can consider sigma Bn as starting from n equal to 5, because from 5th term onwards we can write that an or 1 by n factorial is less than or equal to 1 by 2 raised to n minus 1. N is starting from 5. This is sigma an from n equal to 1 to infinity, and from n equal to 5 to infinity we are getting this relationship. So if we are starting from n equal to 5, then also no problem, we can apply comparison test. So we will check the convergence from n equal to 5 to infinity. So if this series is convergent, then because we are adding finite number of terms in this series, it will not affect its convergence. If this series is convergent and if we are adding finite number of terms, then this series remains convergent. So it is not necessary that an must be less than or equal to bn, or an must be greater than or equal to bn starting from n greater than or equal to 1. Instead of n greater than or equal to 1, we may have n greater than or equal to some fixed number. Then also we can apply comparison test. So this is all about comparison test. In the next lecture we will discuss limit comparison test. I hope you like this. Thank you very much.